So the last lecture dealt with determining or calculating the average rate of a reactant or product, looking at the instantaneous rate, looking at the initial rates. But here we're going to be looking at what's called a rate law. And a rate law shows you how concentration affects the rate. So that's what we're going to be looking at in this lecture, is how do we determine the rate law for a reaction. Again, a rate law for a reaction shows how concentration affects rate. And the rate law is made up of, or the general form of a rate law, let's say we have a reaction A goes to B. Now for the initial rate, we're only going to be looking at rate laws that are for the reactant. So we're going to be looking at the consumption of a reactant over time. So let's say we have the reaction A to B. If we were to write the rate law, the general form would look something like this. So to explain what the different components are, K is referred to as the rate constant. A, of course, is the concentration of your reactant. And M is the order of reaction. And generally, this is a integer. So for example, M could be, the most common ones are 0, 1, 2, 3. And we refer to these as 0 order, first order, second order, third order, etc. So it just keeps on going. But these are the most common ones. So for example, if we had a 0 order reaction, so we have our order of reaction is 0. What this means is that the rate is independent of concentration. So no matter if you change the concentration, it's not going to change the rate of the reaction. And so here the rate constant is in the units, typically molarity per second, because the units of the rate constant have to equal the units of the rate. So that's if it's a 0 order reaction. So if you double the concentration of A, the rate is going to be the same. So it doesn't change with increasing concentration. Now we look at a first order reaction. So rate equals K A to the first. Here rate is dependent on concentration. So what does this mean? This means if we double the concentration of A, this is going to lead to doubling the rate. So if we double the concentration of A, we're going to double the rate of this reaction. And here the rate constant, the units are second inverse. And the way you can determine the units of the rate constant is rate is always, let me write it over here, rate is always the unit meter per second. So whatever is on the right side of the equation is going to have to multiply, so where the overall unit is meter per second. So since A is to the first order, A is molarity, so that means K has to be second inverse, so that we get molarity per second for the units for rate. So that's a first order. Now a second order, we'll explain how we get these orders of reaction in just a moment. Again, rate is, I'll put ditto marks, is dependent on concentration. And so here, if we double the concentration of A, this will lead to quadrupling the rates. So if we double A, rate's going to increase by a factor of 4. Now the rate constant here, since molarity is squared, the rate constant is equal to molarity inverse second inverse. So that way when you multiply it by molarity squared, you get molarity per second. And it's very important that you know the units for the rate constant, because in some questions, they don't tell you whether it's first, second, or third order or zero. They just give you the rate constant and say, given this rate constant, calculate this. So you have to know from the rate constant what are the units represent what order of reaction. And then lastly, we'll look at if it's a triple order. And so again, concentration is dependent, or rate is dependent on concentration. So if we triple, or excuse me, if I say we double the concentration of A, the rate increases by a factor of A. So you can see the higher the order of reaction, the greater the effect concentration has on the rate. And so the rate constant here would be, as you can imagine, meter to the -2, second to the -1, because you're always wanting to get the units of molarity per second out of the rate law. So now we're going to ask the question, how do we calculate rate law? And that's by using the initial rates. So we're going to do a series of experiments, and we're going to measure the initial rates of our reactions. And then we're going to get a list. And again, this is all done experimentally. Well, if the rate is a power of 1/2, or the order of reaction is 1/2, then it would increase the, it would be your rate would be changed by a factor of 1/2. It would be raised to the 1/2. It would be the opposite. But generally, you don't have fractions. Generally, they're whole numbers, or they're greater than 1. So you could have technically a 1.5 order of reaction, but to have it less than 1, highly unlikely. So it should always be 1 or greater, because that means that the concentration, so let's see, we can look at it real quick since you asked. Let's say we have, let's say our concentration is 1, and it's raised to the 1/2. Yeah. So let's say K is the same, K doesn't change, but 1 to the 1/2 is 1. Now let's take the same thing, and we're going to double the concentration. So now we're going to say, instead of 1, we're going to have 2. So 2 to the 1/2, and we get our rate. And the square root of 2 is like 1.41. So it does increase by a factor of 1.41 instead of 1 or 2. That's how you would do it if it was a fraction. So anytime you have a fraction, or you have something that's not a whole number, this is the good way to determine how rate affects, or concentration affects the rate. You start out with 1, raise 1 to that power, and then simulate doubling it by making 2 raised to that power, and you can see how the rate is affected. So now, calculating the rate law, again, this is done from experimental information. So you have to have experimental data to calculate the rate law. And so the way we calculate it by initial rates method is, again, we're still assuming we have this one reactant equation. We're going to do 2 experiments where we're going to have rate 1 equals K A1 raised to the M. So you do an experiment, you have concentration of A, you measure its rate. And then we're going to do a second experiment. So the rate of the second experiment equals the same K. And now we're going to use the second concentration raised to the same order of reaction. So you need a minimum of 2 experiments. In each experiment, you have a different concentration, and you measure a different rate. And then what we do is we need to determine the order of reaction and the rate constant. So the first thing we're going to do is to determine the order of reaction. So we're going to set these up as rate 1 equals K A1 to the M, and then underneath it we're going to do the same thing, but this is a divide sign here. Rate 2 equals K A2 to the M. And so now you'll notice here that the K's cancel. And we can simplify this, since both of A1 and A2 are to the M, we can simplify this to be the following. To be rate 1 over rate 2, and this is in parentheses here, A1 A2. And this is all raised to the M. So now you know what rate 1 is, you know what rate 2 is, you know A1 and A2, you can solve for M. Most of the time, you can actually visually determine what the power of M is. But if you can't, what you can do is, if you take the ln of both sides, then the exponent comes to the front, and you can determine M that way. But this is how you do it for a 1 reactant system. Now, to show you a 2 reactant system, and then after 2, 3, and 4 are the similar processes as this one, but for a 2 reactant system, A plus B yields C. Now, when we're doing this, make note that the order of reaction has nothing to do with the coefficients in the chemical equation. Again, this is all determined experimentally, nothing to do with the balanced chemical equation. So now we do the same thing. We set up our 2 experiments. And when you have 2 reactants, you're going to need a minimum of at least 3 experiments to do it for both. So what you want to do is, when we're determining the orders of reaction for 2 reactants, we need to pick 2 experiments where one of them changes so that we can get the first order of reaction, and then if possible, we pick another set of experiments where B changes and A is constant. So we have K, A1 to the M, B1 to the N. Okay, A2 to the M, one. So again, what you do is if you wanted to determine the order of reaction of A, you have to pick two experiments where A changes and B is constant. So the concentration of B doesn't change. And then once you determine the concentration or the order of reaction of A, then to find the order of reaction of B, the best way to do it is, if possible, pick two experiments where B changes and A is constant. If you can't, then you can still do it. Once you know the order of reaction of one, you can solve for the other. So what happens in this case is that the B's cancel because they're the same, and the K's cancel. So then it simplifies back down to this. And then you would find the order of reaction of A, and then do the same thing for B to find the order of reaction of B. And what you have then is what's called the overall order of reaction, which is M plus N. So we're going to look at a few examples of calculating the orders of reaction. Now, once you have all the orders of reactions, then you can find the rate constant. And the rate constant is a constant. It shouldn't change if you put in different concentration and rate. You should still get the same rate constant for every concentration and rate you get for that particular experiment. This is typically how the problem is arranged. So here we have this reaction where A goes to B, and it says, okay, for this experiment, or for this reaction, we did 3 experiments. We changed the concentration of A and measured the rates. So we want to know what's the rate constant for this reaction. And remember, since it's one reactant, rate is K, A, M. So in order to solve for the rate constant, we have to solve for the order of reaction first. So to do that, you pick 2 experiments, and I'm going to pick experiment 1 and experiment 2. If you did, for example, if you're doing this in the lab, it shouldn't matter what 2 experiments you pick, you should get the same rate constant. If you don't, that tells you that you did something wrong in your experiment. So I'm going to pick experiment 1 and 2, so I'm going to set it up. And so we have experiment 1, and I like to put the bigger number on top, so I'm going to put experiment 2 on top and experiment 1 on the bottom, just so that when I simplify, I get a number bigger than 1, which is easier to determine what the order of reaction is. But whether you put experiment 1 on top or experiment 2 on top, you're going to get the same result. I'm going to put 0.928, 0.034. And then for the concentrations, again, since it's one reactant, it's going to be raised to the M. .15, 0.05. So now we simplify this. we get 26.97 equals 3 raised to the m. So now you have to ask yourself what power of 3 when I raise it to will give me, and that's approximately 27. So 26.97, you can round to 27. And so here m is a power of 3 because 3 cubed is 27. So now we determine the order of reaction. So the rate equals K A to the third. Now to determine the rate constant, you just got to pick one of these 3 experiments, plug in the concentration, plug in the rate, solve for K. Again, to determine the rate constant, you pick one of these 3 experiments. It doesn't matter which one you pick because they're going to give you the same answer. And you plug in A and rate and solve for K. So I'll pick experiment 1. And we can solve for the rate constant. And if you don't have a cube root, you can just do 0.05 times 0.05 times 0.05, or excuse me, cube, you would get the cube of 0.05. And we get a rate constant of about 275. And since it's a third order reaction, this would be m to the negative 2, s to the negative 1. So that would be the rate constant for this reaction. So once you do the rate constant, now you have it for that particular chemical reaction, and you can determine the rate with different concentrations. Example. So in this reaction, we have 2 reactants, nitrogen monoxide and oxygen gas, and we want to know what is the rate when NO is this 0.04 molarity and O2 is 0.03. And it gives us a series of experiments. It says when the concentration of NO is this and oxygen is this, what's the rate of NO2 appearance? So again, what we have to do here is now, since we have a 2 reactants system, we have to determine the orders of reaction for both reactants. And since we're looking for the rate when given concentrations, we have to determine the rate law first. So rate would equal K NO to the M O2 to the N. So we're going to do what we did on the last problem, except we're going to do a duplicate, one for NO, one for O2, to determine the orders of reaction. Once we get the orders of reaction, we're going to determine the rate constant. Once we get the rate constant, then we can plug in these concentrations and solve for the rate at these given concentrations. So we need to pick 2 experiments where NO changes and O2 is constant. So if you look here, experiment 1, experiment 2, NO changes, O2 is constant. So now we can solve for the order of reaction of NO. Set it up. Again, I like to put the larger, the set of numbers for the larger one on top. I'm not including O2 because O2 cancels out because it's the same concentration. So now what do we get? We get 4 equals 2 to the m. So now we can determine what m is. So what power of 2 will give you 4? And the answer is 2. So here, NO is second order. Now we're going to do the exact same thing, but with oxygen. So if we can, we want to pick 2 experiments where oxygen changes and nitrogen monoxide is constant. You don't have to do it this way, but it's better because it simplifies the math. So I'm going to pick experiment 1 and experiment 3. Because notice here, oxygen changes, but NO is constant. So that's going to cancel out. That's going to simplify our calculations. So again, the first one was NO we worked on. The second one is O2. So again, I like to put the bigger one on top. So now this simplifies to 2 equals 2 to the m. So now you have to ask yourself, what power can I raise 2 to get 2? And the answer is, n, sorry. And the answer is 1. So this reaction, O2 is first order, whereas NO is second order. So now you may say, well, how do I know if it's 0 order? The way you would know it's 0 order if instead of a 2 here, there was a 1. So 1 equals 2 to the n, for example, that would be 0. So anything raised to 0 power is 1. So now we have the rate law. We know that rate equals K NO squared times O2 to the first. And now what we need to do is determine the rate constant. So you pick any one of these 3 experiments, plug in the concentrations and rate, and solve for K. I'm going to pick experiment 1. And we're going to solve for K. And we get a K of 25. Now the unit, since this is an overall third order reaction, the unit would be n to the -2 s to the -1, because it's an overall, it's a third order reaction. So now we have the rate constant. We can plug in the concentrations given to us and determine the rate. Rate equals 25 times that'd be 1.2 e to the -3 polarity per second. That would be the rate at the given concentrations. So whenever a question asks you what's the rate at a particular set of concentrations, you have to first determine the rate law by determining what the orders of reaction are. Again, they have no correlation to the coefficients. It's only a coincidence that NO was 2 and the coefficient in front of NO is 2. Again, there's no correlation there. Once you know the orders of reaction, you plug in one of the experiment's information given to you. You solve for K. Once you have K, you can solve for the rate for the given concentrations.